Hi everyone, we're going to continue our discussion of Green's theorem with a couple more examples. So this example, I want to find the integral, the line integral of 3xy dx plus sine x minus y squared dy. Ignore this circle, that's a mistake. This is just a regular line integral over the triangular path from 0, 2 to the origin, then to negative 3, 0, then back to 0, 2. So first, let's take a look at this path. It's going to be 3 line segments. I start at 0, 2, I go down to the origin, I go to negative 3, 0, I go back to 0, 2. Now I'm traversing this path clockwise. This has a negative orientation, which is why there shouldn't be a circle there. That was my mistake. So you would think that we can't use Green's theorem. For Green's theorem we need a positive orientation, but for this path we have a negative orientation. Well, remember, if we switch the orientation of a curve, then we just switch the sign of the integral, right? If we have, we're integrating a vector field, this is true. If we have a scalar function, that's not the case. But for a vector field, that's true. We switch the orientation, we switch the sign of the integral. So if I want to evaluate an integral with a positive orientation and have it have the same value as what I'm looking for, I can just say this integral that I would like to find is the same as the negative version of the curve with a positive orientation. Right? So, and for this integral, I'm allowed to use Green's theorem. So if I'm allowed to use Green's theorem, now I just have to look at this function, take its partial derivative with respect to x, get cosine, subtract the partial derivative of this function with respect to y, which is 3x. So this is minus the double integral over this triangle of cosine x minus 3x. And now I can distribute this negative, and this line integral that I'm asked to find is equal to 3x, the double integral of 3x minus cosine x. So I can use Green's theorem just by kind of a loophole in the rules, right? This has a negative orientation, but if I set up the integral with a positive orientation and put a minus in front of it, that's the same as the one with the negative orientation. So then I can use Green's theorem, and this is the integral I want to find. If I wanted to evaluate this line integral, you could still do that, right? I would just have to set up 3 separate line integrals, one for this line segment, one for this line segment, and one for this line segment. And it would still give me the same answer as this single double integral over this triangle. So it's still possible to find the solution to this problem without using Green's theorem. But this looks a lot easier. It's only one integral. I don't have to worry about setting up parameterizations for each of these line segments. All I need now are bounds for this region D, which I'm setting up over here. So I've drawn the region again. This line segment, the vertical line segment, is described by the line x equals 0. That's the y-axis. The bottom line segment is the x-axis. It's described by y equals 0. And then this line segment between 0, 2 and negative 3, 0, that's described by either y equals 2/3 x plus 2 or x equals 3/2 y minus 3, depending on which direction I want to integrate with respect to first. So I set this up by integrating with respect to y first. So if I integrate with respect to y, I'm going from y equals 0 up to 2/3 x plus 2. Think of moving through this triangle vertically. And then my x bounds are going to be from negative 3 to 0, because negative 3 is the leftmost point, 0 is the rightmost point. So this integral I was asked to find is equal to the double integral, where I'm integrating from 0 to 2/3 x plus 2 and y, and I'm integrating from negative 3 to 0 and x, of 3x minus cosine x. If I integrate with respect to y first, I just get a y here, because this is just a function of x. Notice I can't separate this integral because I have an x in the bounds. So I can't write this as the product of 2 single integrals. So I just have to do an iterate integral, integrate with respect to y, then x. So I get a y here, I need to evaluate that at these bounds. So that gives me the integral of negative 3 to 0 of 3x minus cosine x times 2/3 x plus 2. I'm going to go ahead and FOIL or distribute, however you want to multiply those two binomials together. And that gives me 2x squared plus 6x minus 2/3 x cosine x minus 2 cosine x. Now, for the integral in x, these 3 terms, the first, the second, and the fourth term, I can go ahead and integrate. For this third term, negative 2/3 x cosine x, I'm going to have to integrate by parts. So the next step, I'm just going to rearrange the terms and get rid of this. So in this step, I haven't done anything except rearrange the 4 terms I'm integrating. It's still the same integral. Now I'm going to integrate by parts. So what I'm going to do is let u equal negative 2/3 x. So when I find du, it's just a constant times dx. So then v is cosine, and I integrate, I get sine. So now what I'm going to do is I'm going to integrate these 3 terms and set up my integration by parts. So I integrate 2x squared to get 2/3 x cubed, 6x I integrate to get 3x squared, negative 2 cosine, I integrate to get negative 2 sine, and now here I'm adding plus u times v, where u is negative 2/3 x, v is sine x. So I get negative 2/3 x sine v. All of these functions I now evaluate from negative 3 to 0, and now I subtract the integral of v du. So minus the integral of sine of x, negative 2/3 dx, and I've just taken the minus and the negative and changed it to a plus, the integral of 2/3 sine x. Okay? So now for these terms, I'm just going to start plugging in numbers, and this integral I'm going to evaluate. And I get a bunch of zeros at first, because the upper bound is 0. I get a bunch of terms with negative 3 plugged in here. And then if I evaluate this integral, I get negative 2/3 cosine x from negative 3 to 0. And then the rest is just working it out. So nothing too spectacular here. The only thing I would comment on is this term here. Right, so everything else is pretty standard. I just get some constants here. These sine terms cancel out. Cosine of 0 is 1, so that's where that negative 2/3 comes from. This 2/3 cosine negative 3 is still here. And then in my answer, I've written 2/3 cosine 3. Because cosine's an even function, so the cosine of negative 3 is equal to the cosine of 3. This isn't necessary. You could still write negative 3 here. Your answer would be absolutely correct. I just wrote 3 instead of negative 3. And it's not a typo. So that's your answer. And this example was just to show you that if you have a negative orientation, you can still use Green's theorem. So there's kind of a loophole there. All right. Now, for all of these examples, we've said that our region has to be simply connected. So we can't have holes in our region. But we can extend this to domains that do have holes. And you just say, okay, your curve now is the outer boundary and the inner boundary. And now you can't use counterclockwise to mean a positive orientation. So our definition of positive orientation, where we say it's counterclockwise, kind of falls apart, because if you notice, this inner curve is actually being traversed clockwise. So what doesn't break down is this analogy I talked about in the last video about walking with the domain on your left. If you imagine walking along the curve and having the domain on your left, that's still going to be true for this inner curve here. If I imagine I'm walking on this curve around clockwise, D is still to my left. Okay, so why do we change this to saying the inner curve has to be clockwise, and why do we allow a domain that's not simply connected, right? Remember, simply connected means any loop can be shrunk to a point without leaving the domain, but if I draw a loop here, I can't shrink it to a point without going through this piece that's not in the domain. Well, the trick is actually why I've drawn this dotted red line. The trick is you split D into 2 domains. And so imagine that I have a D1 and a D2 here, and that I'm actually integrating along these red line segments. Now, if I take that point of view and I start traveling along this curve, you'll see that this piece here, where I'm going clockwise, is actually part of this counterclockwise curve, if I include the red dotted line segments. And what's left, this D1, is simply connected. And if I look at D2, I look at the curve going around there. This part of the circle where I'm going clockwise is actually part of this counterclockwise path. And this half is simply connected. And then I just add the 2 integrals together, and what happens to these integrals over these line segments? I'm integrating over these line segments in opposite directions, right? For D1, I'm integrating down, and for D2, I'm integrating up. Same for this line segment. So I'm integrating along the same curve in opposite directions. They cancel out. So you could rewrite this as two separate domains to use Green's theorem. And when you add them together, the line segments they have in common, those integrals would cancel out. So that's why this works. Now I can include regions that have holes in them. But that's a technical detail. What you really need to remember for problems like this is that when you set up your integral, your line integral, you just need to check you have a positive orientation so the domain's always to your left if you were to walk along that curve. Okay. So here I've just rewritten it. So now my curve for the line integral is this C1 curve, the outer boundary. Together, this union sign is just meaning these two curves together. So it's kind of like a plus sign for curves, or sets rather. But in this case, our sets are curves. Plus C2. But now to have a positive orientation, it has to be moving clockwise on the inside. And then this line integral is equal to this double integral of the kth component of curl. So let's do an example. So let D be the region inside the ellipse x squared over 9 plus y squared over 4 equals 1, and outside the circle x squared plus y squared equals 1. Evaluate this line integral where the curve is well, I think I've still got it covered up. The curve is the boundary of the domain, and it needs to have a positive orientation. So I've gone ahead and drawn this. First, to draw an ellipse, right, you have two axes, and they're just the square roots of the numbers under x and y. So in the x direction, and this is centered at the origin, in the x direction, my axis is 3, or my major semi-axis. In the y direction, my minor semi-axis is 2. So I'm going to go out 3 from the origin in the x direction, 2 from the origin in the y direction. And then the circle is just centered at the origin, radius 1. So this is what the region looks like. In order to have a positive orientation, I'm going around this ellipse counterclockwise, and I'm going around the circle clockwise. And so if I wanted to compute this line integral, I'd have to set up two parameterizations, make sure I'm going along those curves in the correct way. But I can use Green's theorem and just integrate over this region between the circle and the ellipse. And if I do that, I take the appropriate partial derivatives. So this partial derivative with respect to x is 2x plus 2. This partial derivative with respect to y is 2x. I subtract them. I just get the integral of 2, which is twice the area of this region. So you could switch to polar coordinates and use polar coordinates to figure out this region. I'm just going to use geometry and say, okay, if this is just twice the area of this region, then this is just twice the area of the ellipse minus the area of the circle. That's the area in between the ellipse and the circle. So I'm not even going to integrate. I'm just going to use geometry and say, okay, well, I need to know what the area of an ellipse is. And the area of an ellipse is the product of the two axes, the two kind of radii type things, times pi. And let's just say I give that to you. And the area of a circle is pi r squared. So in this case, my major semi-axis is 3, my minor semi-axis is 2. That's how far out I'm going in the x and y directions. And my radius for my circle is 1. So this ends up being 10 pi. And that's it. So rather than talk about Green's theorem for flux, I think I'll save that for another video. But that's all we have left for chapter 16.4, the second version of Green's theorem. And that'll be in the next video.